So the study requires accelerators to accelerate the particles, detectors, basically big digital cameras to work out what happens when they collide, enormous computing resources to analyze the data that we get from the detectors, and also massive collaborative effort. Thousands of scientists, engineers and technicians building and operating these very complex machines. So the elements of innovation in science, and I say that large science projects, they're not the only way of pushing innovation in science, of course, but they do push it on all kinds of fronts. The space missions are fairly famous for doing that in particle physics accelerators in general, and the Large Electron-Positron Collider, which was in the tunnel before, the LHC, and now the LHC, are the key there. Just some words. I will have time to look at the details of one or two more of these, but these are all areas where CERN has pushed the technology in order to, and CERN and its collaborators have pushed the technology in order to deliver the LHC. High magnetic fields, vacuum, precision alignment, cryogenics. Assembling this massive high-tech jigsaw puzzle from all around the world is actually a highly non-trivial engineering problem and logistics problem. High-density radiation-tolerant silicon detectors for studying, getting very close to the beam and see what happens in the collisions. Large-scale industrial control systems. You don't want the professors able to screw the whole thing up by pressing the wrong button, for instance. Electronics and computing systems, project management and coordination. All of these things are real challenges that have to be met in order to find out what's going on at the electroweak symmetry breaking scale. A few examples of the technology from this project. Superconductivity. There are new magnetic resonance imaging is now being developed using LHC magnet technology. Components from the cryogenics at the LHC are now being deployed at ITER. This is a particularly interesting one because the components were developed by the French nuclear industry, industrialized at CERN because the LHC was so big, and then now they're industrialized, they're being deployed at ITER for fusion research. Positron emission tomography, if I have time, I will come back to that at the end, but some of the crystals developed for CMS are being used in detectors for that to make the whole thing cheaper, and the same technology, as they're now being used in medical imaging. And the grid technology, you'll hear more about eScience and the grid and son of grid after this. The accelerator, I mean, one of the surprisingly, actually, I think the main challenge in the accelerator is not actually accelerating the particles in energy. It's actually keeping them in the ring. So, Newton says they want to carry on straight. They're going at very high energies. To make a very, very high energy particle bend, you need a very, very powerful magnetic field. And those are the components, these cryogenic magnets operating at 8.3 Tesla. They're supercooled, superfluid helium, huge cryogenic system. And they're under better vacuum and at lower temperature than interplanetary space. And just to give you the context, it's the first fully superconducting accelerator, which is related to why it's about a year late compared to when we started, of course. I can talk about the problems if you want afterwards. But it's a factor of 7 higher than previously achieved in energy and a factor of 30 times higher in terms of number of interactions. Just to say a little bit more about the cryogenics, this liquid helium is a very unusual substance. It displays two phenomena which are both pillars of the design of the LHC. Not long ago, these were cutting-edge condensed matter physics, and now they're being used in engineering, in particle physics. The interchange between the areas of science and engineering is amazing. Without detailed knowledge of these, the LHC just would not work. 100 years ago, helium was first liquefied, and today we've got 32,000 litres of the stuff going in liquefied every hour by these big cryogenic plants. It's the biggest refrigerator in the world, and as I say, this whole technology has been pushed, actually not in terms of fundamental physics, but in terms of industrialization and scale of this kind of thing by the LHC. So that's kind of an example of the extreme requirements in several domains. If it doesn't exist and we need it, we have to invent it, and we have to do it within basically at best a flat budget. And we look around at what exists, we innovate and automate to drive the cost down. Another example of this is the high level of high radiation level and the development of electronics, readout electronics for the detectors that was driven because of that. I said it's collaborative in a big way. These are the biggest and most sophisticated detectors ever built. It's taken 2 decades to design and conduct the R&D, and it will be another 2 decades understanding the physics we get from it. This is the list of CMS, since these slides are 90% Jim Verdi's slides, in fact. And so, although I'm on Atlas, I'm showing you the CMS collaboration here, but we have a similarly long list for Atlas. what are the people that another way we impact on innovation, I guess, in this is what the people that we produce, if you like, or that we train. The PhD students in particle physics have a very wide array of destinations, a large fraction going into industry, obviously quite a few staying in research in universities or research centres, and then other. If you look at the industrial breakdown of where they go, contrary to popular mythology, the financial crash isn't entirely our fault. In fact, I've got friends who said if there was more particle physics PhDs and less MBAs, it wouldn't have been quite as bad, but there we are. The computing is a big destination, other, of course, here, but electronics, chemistry, consulting, communications, these skills that people pick up in these huge collaborations are in demand all over the place. This is the destinations for people from one of the experiments on the previous machine at CERN. LHC media events, there's a huge public interest in this, and that drives interest in science and engagement with science in an increasingly powerful way. In 2007, 200 million people watched CMS being lowered down into the hole where it's now operating. When we tried it starting up for the first time, the footage was watched by an estimated 1 billion people, slightly less watched when it broke down. And then we started again this March. We had 2,200 at least news items published. I think this is just the people who check back with CERN and say, can I use your material? A lot of people don't. Here's an example of some of the places it appeared. Here's me talking to Jon Snow, and I put it up just because I was so impressed they matched the background to my shirt. I thought it was brilliant. It has societal impact all over the place, even in opera. This is an the Atlas detector in Les Troyens. By Berlioz. I didn't see the opera, but I'm told it was very good. And apparently Lost is going to feature CMS in a big way in the next series. This is from Jim. I don't know about this. I didn't tell you. I have no idea. But apparently that's true. And, of course, angels and demons and things. It's something you no longer have to explain. You can use CERN and the LHC as a tag meaning high-tech, super cool science in the same way you can use NASA or something, which 2 years ago you certainly couldn't. And I think that's good for all science, that we get more and more of these exemplars out there. I'll just give you, in the last few minutes, some pictures to illustrate, because you can say how complex it is, but I think maybe those of you who are used to building and looking at high-tech kit, it may be worth just showing a few pictures in case you haven't seen them. So this is the classic picture, which I think the best place it ever ended up was a centerfold in FHM for some reason. From 2005, it's quite old now. This is a standard European technician engineer there in the middle. These are the magnets that are part of the Atlas detector, and this is now full of Atlas detector underground and functioning. This is part of CMS being put in. If you look at the kind of level. On the Science and Technology Facilities Council, there are a lot of industrialists. Some of you may even be here. One of the comments I got showing one of these people around was, it's like building an oil rig one-off for a laugh. Just getting 50 countries, 150 universities to collaborate together and build an oil rig from scratch. He said I think the guy was working in oil. That was his example, and I thought it was it quite impressed me. I didn't realise oil rigs were that high tech, actually, but it's certainly a very challenging. You can see that if you don't have very good processes and very good engineering and very good everything from databases and checking to make sure that all these connections go to the right place, for instance. I remember that once these things are underground, you don't touch them. It's almost like firing them up in a satellite, because you can't get down there. They've got to work from then on. This is the results we're starting to get. This is one of the first W. Remember, the W was the force carrier of the weak interaction. We want to be producing a lot of those because we're well above the energy of the W mass. That's the whole point of the LHC. This is one of the first ones in an event display, which I can't resist mentioning was written by UCL people. This is one of our contributions to Atlas. But we're hoping for many millions more of these.